Let's now look at the evidence for the Big Bang. You have already heard that there is a cosmic microwave background that is a Planckian at a temperature of about 2.7 Kelvin above absolute zero. And if you remove this Planckian from the cosmic microwave background, you see the fluctuation on top of it, which is of the order of 10 to the minus 5 of the original intensity, which gives you the origin of structure in the universe. But let's dial back a bit and see how the Friedmann equation leads to the conclusion that there must have been a Big Bang. Indeed, one of the main results of cosmology, the Big Bang, was predicted long before the observational evidence for it was found in the form of the cosmic microwave background radiation. This result was predicted by Georges Lemaitre, who called it the hypothesis of the primeval atom. And the prediction comes out naturally from Hubble's law. In fact, Lemaitre was the first one to propose what we now call Hubble's law. It is sometimes called Hubble-Lemaitre law for this reason. Let's consider the critical density. You can write the ratio of the measured density to the critical density by defining the parameter omega, which is the density over the critical density. Given the definition of the critical density, then omega is 8 pi g rho over 3h squared. We can use this quantity to write the Friedmann equation more compactly. If we substitute the second term in the left-hand side by omega, then the Friedmann equation becomes h squared multiply 1 minus omega times the square of the scale factor, then is equal to minus kc squared. So the conditions for the universe to be closed, open, or flat can be written now in terms of omega. So we can measure the present value of this quantity omega, call it the density of the universe as of now, over the value of the critical density as of now. That translates into simply measuring the density of the universe at present and the Hubble constant at present. And again, we can substitute the constant k by writing the Friedmann equation at present. Present then a is equal to 1. And then you have node subscripts for omega and the Hubble constant. That means you can substitute k as minus omega naught squared, 1 minus omega naught over c squared. Doing that, and then substituting this k into the Friedmann equation, you can write the Friedmann equation in a form that looks strange at first, but will make sense. What's interesting about this is that on the left-hand side, you have quantities at any given time in the universe, and on the right-hand side, only the quantities at present. Now, if you substitute the definition of the scale factor in terms of the redshift, then you can write this equation in terms of redshift as, and this is even more interesting because on this equation here, you cannot measure the scale factor at a given time, but you can measure the redshift of any object at present. So on the right-hand side are all quantities that you can measure, and on the left-hand side, quantities that you want to know. Now you can solve this for h. And an immediate result from this equation is that as the redshift goes to infinity, then the Hubble constant also goes to infinity. That is, as the scale factor goes to 0, the rate of expansion goes to infinity. That means that if the universe had 0 size, the rate of expansion was infinity. You can think of a rate of expansion equal to infinity as similar to an explosion. So that means that if the universe had 0 size, then there was a Big Bang.